Okay, good afternoon, everybody. Thank you all for coming to this afternoon's distinguished lecture. So allow me to introduce David Woodruff. We're very lucky to have him visiting us from IBM Almaden. He very nearly didn't make it. He took 3 flights to get from San Jose to Vancouver last night, arriving at 1 a.m. So if he appears to be a little bit sleepy, we know the reason why, but hopefully the material will engage us all. So David is a theoretical computer scientist working in a wide number of areas. He started off working in crypto and coding theory, and during his PhD, he also worked in streaming algorithms. And so at this point, I'm pretty sure for most streaming problems, either the best known upper bound or lower bound is probably due to David, and sometimes both are due to David. He got his bachelor's from MIT in 2002 and his PhD from MIT in 2007 under the supervision of Piotr Indyk. And he also did a one-year visitor at Tsinghua University in 2005, and he's been at IBM Almaden since 2007. He's won several awards, including the best paper at PODS in 2010 for his lower bound on the distinct element problem. Upper bound on the distinct element problem. Is the lower bound also yours for that? Yeah. Okay, all right, as I suspected. And also best paper in Stock 2013 for his more recent work on randomized numerical linear algebra. So David is really one of the central figures in this new community looking at randomized algorithms for lots of numerical linear algebra problems. And we're very lucky to have him talk to us today about that. So please join me in welcoming David.
So thanks, Nick, for the introduction, and I'd like to thank UBC for inviting me here today. I'm going to talk about sketching as a tool for numerical linear algebra. So I'll go over some very well-studied problems in numerical linear algebra. I'll go over classical solutions to these problems and show how you can use techniques called sketching that are inspired from different areas in theoretical computer science, such as data streams, to speed up algorithms for these linear algebra problems. So, and one reason you want to speed up these algorithms is because these days you have very massive data sets. So the classic examples are internet traffic logs, financial data, etc. And so you want nearly linear time, or sometimes even sublinear time algorithms on these data sets. And in order to achieve this running time, this usually comes at the cost of a randomized approximation. That if you want a deterministic algorithm or an exact algorithm, usually the algorithms are too slow to be practical. So the first problem I'll talk about in linear algebra is the problem of regression, which is just a statistical method to study dependencies between variables in the presence of noise. So in particular, I'll focus on linear regression, which studies linear dependencies between these variables. So a simple example of this problem is Ohm's law, where the voltage is the resistance times the current. And what you get are a bunch of voltage-current pairs, and you're trying to find an unknown line. In this case, it's just the unknown resistance, which goes through these voltage-current pairs as best as possible, according to some notion of fitness. And I'll describe several different notions of fitting a line to points throughout the talk. Okay, so let me state it a little bit more abstractly. So in the standard setting of linear regression, there's one measured variable b. In the previous example, this was the voltage. And there's a set of predictor variables, a1 through ad. So in the previous example, d was equal to 1, and a1 was just the current. And the assumption is that the measured variable B and the predictor variables A1 through AD are linearly related up to some noise parameter. So what that means is that B is equal to x naught plus A1 x1 plus dot 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 AD xd plus epsilon, where the xi are the unknowns that you're trying to solve for, called model parameters, and epsilon is noise, and we don't want to assume anything about epsilon if we don't have to. So it could be worst case noise. We would like algorithms to work in that setting. It could be from some distribution we know or some distribution that we don't know. And so the goal is to come up with these values xi. Via standard transformation, you can assume that this free term x naught is equal to 0. So let's not include that term. And now let me just recast this problem in the form of obtaining n measurements. So usually, you have multiple voltage current pairs, you have multiple observations. So let me just write the problem in matrix form. So as input, what you're given is an n by d matrix A. So the rows correspond to these n observations. The columns correspond to these predictor variables. And you're given a vector B, B1 through Bn, of the observed voltages, say. And what you're trying to do is find the coefficients of this vector x star so that A times x star and B are close, under, again, some notion of closeness. And I'll go over a few of those. Okay, so throughout the talk, we're going to consider the over-constrained case, when the number of observations is much larger than the number of predictor variables. So there needn't be a solution to this equation, AX equals B. This is a popular case. You can assume that actually A has full column rank. There's a very efficient algorithm for finding a subset of the columns of A which are linearly independent. I won't go over that, but let's just assume that the columns are linearly independent for this talk. Okay, so what are some ways of solving regression? So what are some notions of fitness that we have? So there's the least squares method, which is probably the most popular method of regression, which is that you want to find x star, which minimizes the Euclidean norm between Ax and B. Right, so the sum of squares over the observations of the difference from what you observe and what you predict by the inner product of the ith row of A and X. So this has certain desirable statistical properties. If your noise is Gaussian, this epsilon is Gaussian, independently in each observation, you can show this is a maximum likelihood estimator. And another form of regression, which is less common, but it has certain robustness guarantees that least squares regression does not, is the method of least absolute deviation, or L1 regression. And the only difference here is instead of looking at the Euclidean norm between Ax and B, we look at the absolute value, the sum over absolute values, so the one norm between Ax and B. So the absolute value of what you observe minus what you predict. And this is less sensitive to outliers because you're not trying as hard to fit very high noise observations with a lot of noise. Since you're not squaring them, you're not trying as hard to fit them. It's less sensitive to large values of noise. Okay, so these are two notions that we'll go over, I'll go over throughout the talk. Let me just say one more way of thinking about regression to make sure that we're all that we all really understand this problem well. So the geometry of regression, again, we want to find this x that minimizes the p-norm between Ax and B for p1 or 2. And what is Ax? Well, I can just expand this in terms of the columns of A. So it's the first column A star 1 times x1 plus the second column A star 2 times x2 plus dot 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 the dth column of A times xd. So what is this? as I range over all possible x, all possible solutions, I range over all vectors in the span of the columns of A. So all we're really doing is we're saying we want to find the closest point inside of the span of the D columns of A to this vector B that we're given. So if P was equal to 2, this is a Euclidean norm, then all we're doing is we're finding the projection of B onto the span of the columns of A, in the standard notion of projection. For the one norm, we're finding the L1 projection, which is a bit less standard. But this is sort of the geometry of the problem. And let me now give exact solutions for both of these problems, which are polynomial time, but they won't be that efficient for massive data sets. So how do you solve the least squares regression problem? So you can solve this problem via the so-called normal equations. So this is the problem we're trying to find, trying to solve, and you can solve it exactly. So the normal equations, what they are is they say that for the optimal solution x, that A transpose AX equals A transpose B. This is a condition you get by looking at the gradient. So this is the normal equation, and this is what the optimum solution satisfies. Now, we said that A's columns are linearly independent. We can assume that without loss of generality. So what that means is A transpose A is a full rank square matrix. And so I can just solve for the x that is an optimum solution for least squares regression. X is just equal to A transpose A inverse A transpose B. Okay, so one nice thing about least squares regression is there's a closed form solution, and it's not that hard to compute it. I mean, the dominant cost is computing A transpose A. It's a matrix-matrix multiplication. So that can be done in ND squared time. At that point, A transpose A is a small square matrix, D by D. And you can compute its inverse in D cubed time, say. And so basically the dominant cost is really this matrix-matrix multiplication. It's ND squared time, which is reasonably efficient, but it's not very exciting if you have massive data sets. N is very large, and that's sort of the motivation for this work. What about L1 regression? So L1 regression, you can solve by casting the problem as a linear programming problem. So how do you solve L1 regression as a linear programming problem? So you want to minimize the one norm between AX and B. And what you can do, the L1 distance between AX and B, what you can do is introduce 2n new variables. So two vectors, alpha plus and alpha minus, each which are n-dimensional. And you can put the constraint that these two vectors are non-negative. And then what you can do is you can minimize the inner product of the all ones vector with the sum of alpha plus and alpha minus. So why does this capture L1 regression? Well, the reason for this is that if I look at any given coordinate of AX and the same coordinate of B, then since I have equality here, I need to either set alpha plus or alpha minus to be the difference between those two coordinates to get this equality. And because I'm minimizing this objective function, it's best for every coordinate to set one of alpha, so either set alpha plus's coordinate to be non-zero and alpha minus's coordinate to be 0, or alpha plus's coordinate to be 0 and alpha minus's coordinate to be non-zero, depending on the sign difference of that coordinate in AX and B. So basically all I'm saying is that you can write down the L1 regression problem as a simple linear program. The number of variables is order n plus d. The number of constraints is order n. And then you can just use your favorite LP solver to solve this problem. And this will take polynomial and nd time. And if n is much larger than d, it's actually at least n squared time because you have both at least n variables and n constraints. So this is quite prohibitive for large values of n. So those are the exact solutions for least squares regression and L1 regression. And in the remainder of the talk, what I'm going to do is show how you can get significantly faster algorithms for these problems using sketching. So first for least squares, then for L1 regression, and then for low rank approximation, which is a problem related to least squares regression. Okay, so let's first look at how we can use sketching to speed up least squares regression. Okay, so as I said at the beginning, we're not going to require an exact solution. We're instead going to allow randomization and get an approximate solution. So what does that mean? Well, we'd like a relative error solution. So we'd like to, instead of outputting the optimal x, we output x prime, for which the Euclidean norm between ax prime and b is at most 1 plus epsilon times the least squares cost solution with high probability. Okay, so how can we do this? So here's the following methodology, which I like to call sketch and solve. So what does it mean? So what we're going to do is we're going to choose a random matrix S from a k by n random family of matrices, where the number of rows k is much smaller than the number of columns n. So this is a very wide fat matrix. And I'll discuss different random families that work and are useful soon. And the idea is simply to compute S times A. So S is a wide fat matrix, A is a tall thin matrix. I compute S times A and I get a very small squarish looking matrix. I compute S times B, which reduces this n-dimensional vector B down to k dimensions. And all I do is I now solve exactly this much smaller instance of regression, which I can afford to do since it's so small, say by using the normal equations, the solution I talked about earlier. So I just replace A with S times A, replace B with S times B, and I solve this problem exactly. I get some vector x prime, and the claim is that vector is a good solution to the original problem. If I plug it into ax minus b, I will get a 1 plus epsilon approximation with high probability, provided I choose my random matrix S from a family of matrices that work. Okay, so the natural question here is when does this work? Which matrices S will give us this guarantee? Okay, so we want this to be a 1 plus epsilon approximation. It turns out that lots of random families of matrices work. In particular, if S is a d over epsilon squared by n matrix of IID normal random variables, this will give you a 1 plus epsilon approximation with high probability. So S is this matrix. It's very dense. Every entry is a standard normal random variable. Okay, so that gives a way of reducing the problem to something small, but have we really gained anything? Because the problem is that computing S times A may be very slow. Right, so S is a d over epsilon squared by n matrix. It's dense. A is an n by d matrix. Naively computing this matrix-matrix product is even more than nd squared time, which we could have used to solve the problem exactly. This is nd squared over epsilon squared. Or I mean even, yeah, so nd squared over epsilon squared using naive matrix multiplication. So we haven't really gained anything by doing this. But a very nice paper of Thomas Sarlos showed that instead you can choose these random families of matrices S from much more structured families of matrices, which enable for fast matrix-matrix multiplication. So what S can be is a so-called fast Dalton-Lindenstrauss transform. Now what is a fast Dalton-Lindenstrauss transform? So it's a random matrix. It typically has the following form, that it can be expressed as the product of three matrices, PH and D, with the property that these matrices can be very quickly applied to a vector. You can multiply them by a vector very quickly. So what are these matrices? So D is a diagonal matrix. And on the diagonal, for each entry, independently with probability 1/2, I set it to 1, and with probability 1/2, I set it to -1. So this is a random matrix that can be applied to an n-dimensional vector in order n time. What is H? H is a fixed matrix. H is just the Hadamard matrix. It's an n by n matrix. It's dense. But a very nice property about H is that you can multiply H times an n-dimensional vector in n log n time. So H has a special form which allows this to be possible using the fast Hadamard multiplication. And what is P? P just chooses a random small subset of rows of H times D. So if I'm applying S to a vector, I first compute D times that vector. It has the same dimension n. Then I compute H times that product, which is dimension n. And then P will just choose a random subset of coordinates of that vector. And since this can be applied to a vector in n log n time, I can compute S times A much faster. So for each of the D columns, I spend n log n time. Overall, I spend nd log n time. And using the connection to regression, this gives an algorithm for regression, which is nd log n time, which is already much faster than the nd squared time of solving the problem exactly. So I won't prove why this works, like why it's guaranteed to give a 1 plus epsilon approximation. But the intuition is that what you want to do with S is to preserve Euclidean norms of a vector. You apply S to a vector and you want to preserve its Euclidean norm. And that's what's needed for the regression argument to work. Now what's one natural way of trying to estimate the Euclidean norm of a vector? Well, you can just sample coordinates of that vector. And you can scale up your samples, and that will be an unbiased estimator for the Euclidean norm. But that's a very bad algorithm if your vector is sparse, because you're most likely going to sample zeros and you won't have any clue what the actual Euclidean norm of your vector is. Well, so that's what the point of this H is, this Hadamard transform. So if you have a very sparse vector, then by so-called uncertainty principles, if I apply H to a sparse vector, then it spreads out the Euclidean norm across all of the coordinates. And so now random sampling will work, will be a good algorithm for estimating the Euclidean norm. Of course, you can't do it deterministically. Otherwise, I could apply this to, say, H inverse of a vector. So I need this matrix D to introduce some randomization there. And that's basically the intuition of why this works for estimating the Euclidean norm, which is good for the regression problem. Okay, so that's the fast Johnson-Lindenstrass transform. And the natural question is that the best we can achieve? So we achieved nd log n time. The size of your input matrix A is n by d. Is that the end of the story? Well, in many applications, your input matrix A is actually a sparse matrix. It's n by d, but it might only have 3n non-zero entries. And so what you could hope for is to achieve an algorithm with a leading order term of order n, rather than order nd, or more precisely, order number of non-zero entries of your matrix A. And it turns out that you can actually achieve this. So instead of choosing S to be a matrix of normal random variables, or fast Johnson-Lindenstrass transform, you can choose S to be a so-called count sketch matrix, which is a matrix that was used in the streaming literature for finding heavy items in a data stream. So a completely different context. So what is this matrix S, this random matrix? It's again a k by n matrix, where k is much less than n. It's a very wide, fat matrix. The value of k is a little bit larger than d over epsilon squared. Now it's d squared over epsilon squared, still independent of n. And the nice property about S is that it's very sparse. It's almost entirely zero. So what does S look like? So this is a picture of S. And all it is for each of the n columns, I do the following process independently. For each column, I choose uniformly at random among the k entries a position which I'm going to make non-zero. All of the other positions I make 0. And on that position that I've chosen, I put 1 or minus 1 independently with probability 1/2. So that's the matrix S. And you see that since it's so sparse, you can compute S times A in time proportional to the number of non-zero entries of A. Because for each column of A, I look up its non-zero entries, and those correspond to columns inside of S, and there's only a single non-zero entry in each column of S. So I can compute S times A proportional to the sparsity of my input. And the surprising part about this is that it actually works. That for this choice of K, d squared over epsilon squared, if you do this, you compute S times A and S times B, and you solve this regression problem in the sketch space, then you're guaranteed to get a 1 plus epsilon approximation with good probability. So I won't give the proof of that, but this proof really uses the fact that you're applying S to a subspace. This turns out not to be as strong as the Johnson-Lindenstrauss transform. That it doesn't preserve Euclidean norms of arbitrary vectors with very high probability. But it does preserve all Euclidean norms in a low-dimensional subspace. And that structural property is crucial for arguing that this matrix works. And then here the subspace is the column space of A in the regression problem. Okay, so actually this is the state of the art for L2 regression, that you can get ordered number of non-zero entries of A plus a term which is polynomial in d over epsilon. So the leading order term, yes?
Did you also to put a restriction in that every row of S has at least one non-zero element, or are you just assuming that that happens with high probability?
That happens with very high probability, yeah.
Okay. Right.
So. And if some row of S didn't have, was 0, you wouldn't need to include it in the, you could just delete that row. Okay, so that's least squares regression, how we use sketching to go from an ND squared exact solution to an order n solution in the case of sparse matrices. Okay, so next let me talk about a little bit more complicated way of using sketching, which is for this L1 regression problem, this robust version of regression. So recall that we're trying to minimize the one norm between AX and B. And again, we have the same notion of approximation, that we want a 1 plus epsilon approximation, a relative error approximation, but with high probability. And what is the natural attempt for trying to solve L1 regression now that we've seen how to solve L2 regression? Well, the natural attempt is to draw a random matrix S from a k by n family of matrices, which is very wide and fat, for a small value of k, compute S times A, compute S times B, squish the L1 regression problem down to something small, and just solve this new regression problem exactly using linear programming, as we said we could do, and it's small now, so that's efficient, and use that solution and plug it into the original problem. So this is a very natural thing to try, and it turns out that this does not work. At least with respect to known techniques, it does not work. And let me say why on the next slide. So why can't we just do this sketch and solve for L1 regression? So it turns out that we just don't know of matrices S which have this property. That, if you were to, don't know of matrices S with a small value of k, for which if you were to solve this problem in the sketch space, that you would get a 1 plus epsilon approximation with high probability. So there are algorithms where the sketching matrix S has dimension, which is d to the order 1 over epsilon. It's exponential in 1 over epsilon. It's quite prohibitive in practice. On the other hand, this is an interesting open question. We don't have a lower bound saying that there don't exist random families of matrices S which do have this property. So that doesn't work. Instead, what we can do is we can find a random family of matrices S with the following weaker notion of approximation. if we solve the problem in the sketch space, then what we get, instead of a 1 plus epsilon approximation, is a d log d approximation. So that might not be very exciting, but at least this approximation doesn't depend on this large dimension n. So it's a d log d approximation, but it turns out that we're going to see that we can use this approximation and combine it with a sampling step in order to get a 1 plus epsilon overall approximation. So let me describe that. But before I do so, first we need to know which random families of matrices S work for giving even this weaker notion of approximation, this d log d approximation. So it turns out that what S can be is a matrix of IID Cauchy random variables. Okay, so for L2 regression, IID normal random variables would work. So what is a Cauchy random variable? So here is the probability density function of a Cauchy random variable. They're not very nice, not nearly as nice to work with as Gaussian random variables. And the main reason for that is that they have very fat tails. So they decay much slower than Gaussians, which have an exponential tail. And because of this very slow decay, these very heavy tails, you can show for Cauchy random variables, they don't have an expectation. You can try to integrate to compute the expectation, the mean, and you'll get an integral that doesn't converge. You can try to compute the variance of these random variables. The variance is infinite. So these Cauchy random variables don't really seem useful for much. And one question is, like, can we even generate one of these random variables? Otherwise, how do we create the sketching matrix S? So that at least you can do. It turns out that the ratio of two independent normal random variables is a Cauchy random variable. So we can at least generate these things. Okay, so what is the intuition, why a Cauchy random variable is useful for L1 regression? So to answer that question, we should first ask why normal random variables were useful for L2 regression. So the reason is a so-called two-stability property. But all that means is that, as you might have seen, if I take the sum of two independent normal random variables, I get another normal random variable. And the variance of the two normal random variables adds. So if I take a normal random variable with variance sigma 1 squared and a normal random variable with variance sigma 2 squared, and I add them up, I get a normal random variable with variance sigma 1 squared plus sigma 2 squared. So in some sense, normal random variables are good because you can think of these variances, sigma I, as being the square. Sigma I squared is the square of a coordinate of a vector you're trying to estimate. And the reason that Cauchy random variables are useful is because they have an analogous property for L1. If I take a Cauchy random variable times a number, plus another independent Cauchy random variable times a number, and I add them together, I get a new Cauchy random variable scaled by the sum of the absolute values of those two random variables. And that's why that is useful for L1 regression in the same way that normals were useful for L2 regression. Okay, so this is Cauchy random variable, and we said we can use a matrix S of Cauchy random variables for trying to solve L1 regression. And what we get is if we choose this matrix S to have d log d rows and n columns, then if we replace the matrix A with S times A and B with S times B, and solve the L1 regression problem in the sketch space, we get this d log d approximation. Okay, so how are we going to use that to get a 1 plus epsilon approximation? So we can first solve this problem, and for this very poor solution, x prime, which is a d log d approximation, we can let b prime equal ax prime minus b. So the one norm of b prime we know is a d log d approximation. That's what it means for x prime to be a solution, to give a d log d approximation. And now what we can do is we might as well solve the regression problem instead of with A and B, with A and B prime. This is the same regression problem with just a change of variables on x. Because I can just replace x with x plus x prime. Okay. Okay, so now what do we do? So now the main idea here, and it's more complicated than for L2 regression, is to use sketching as a form of preconditioning of your matrix A, so that the following natural procedure for L1 regression would work. So what is one way of solving regression? So one way is just to sample a few rows of A and the corresponding entry of B and solve regression on the samples, and to scale that up. So that will fail very miserably if your matrix A is ill-conditioned in a certain sense. So the goal of sketching for L1 regression is to try to find a good conditioning of your matrix A so that this natural sampling algorithm will work. So let me just describe what the algorithm is. So the algorithm is you compute S times A, and then you compute, which is a very small matrix, d log d by d, and you compute a QR factorization of S times A. So what does that mean? So for any matrix S times A, I can write it as the product of a matrix Q with orthonormal columns and a matrix R. So the standard notion of L2 orthonormal columns. So I compute a QR factorization of S times A, which I can do efficiently now that I'm in this much lower dimensional space. Because usually a QR decomposition would take a lot of time, like nd squared time. But I've reduced the dimensions. And now it turns out that if I just look at A times R inverse, then this is a well-conditioned matrix in the sense that this natural sampling algorithm will now work. So what we did is we used sketching to find this R inverse so that sampling would work. So the algorithm is just the following. We use sketching to find this R inverse. And now if we sample a small number of rows from A times R inverse, and the corresponding entry in B prime, our poor solution from the previous slide, if we sample these rows and just solve L1 regression on the samples, we'll get a 1 plus epsilon approximation. And you have to do a little bit of reweighting. So you sample proportional to their 1 norm. And you scale back by the reciprocal of the probability that you sample with. So you have an unbiased expectation. But so the point here is really that you use sketching in a different way. You use it in a way to precondition your input matrix so that sampling would work. Okay, so that is all I have to say about L1 regression. Well, I mean, so this, I won't say why this works in any more precise way. I just wanted to give you an illustration of different ways of using sketching for your problem. But okay, so the main caveat behind this, it turns out that the most expensive operation in this whole process is computing S times A. You know, all these other steps, they sounded complicated, but they were performed in this low dimensional space. So they're easy. The main thing is just computing this dense matrix of IID Cauchy random variables times A. You know, just like for L2 regression, this was the bottleneck. All other operations are in the smaller space, and perhaps unsurprisingly, you can speed this up by choosing S from a much more structured random family of matrices. So instead of a matrix of IID Cauchy random variables, what you can do is choose a random count sketch matrix times a diagonal matrix of IID Cauchy random variables. So this matrix, suppose I set S to be this matrix, then I can compute S times A very quickly now. We said that it's easy to multiply a vector by a diagonal matrix. And we said that count sketch can be applied to a vector and number of non-zero entries of that vector time. So now I can compute SA very quickly, and it turns out that this matrix S gives you the same 1 plus epsilon approximation as using a dense matrix of Cauchy random variables. And there are, in fact, further optimizations to this. One thing you might try to optimize is the number of samples you need after you do your preconditioning. And, so in the second step of the L1 regression algorithm. It turns out that you can choose S if instead of the diagonal matrix of Cauchy random variables, you choose reciprocals of exponential random variables on the diagonal. Then you can slightly reduce the sample complexity in the second part of the algorithm. So this sketch, what it is a count sketch times a matrix whose diagonal entries are reciprocals of exponential random variables. So there are all kinds of random variables, all kinds of distributions that are useful for sketching. And this is just another example. So that's basically the state of the art for L1 regression, that you can achieve an algorithm which runs in time proportional to the number of non-zero entries of your input matrix A, plus a lower order term, which is polynomial in the small dimension. Okay, so that's L1 regression. And finally, let me just briefly mention application of sketching to low rank approximation. Okay, so low rank approximation is another well-studied problem in linear algebra. Think of being given as input an n by n matrix A. It doesn't need to be square, but let's just suppose it is. And typically in applications, A is well approximated by a very low rank matrix. That is, it might have started off as a low rank matrix and only have high rank because you added noise to it. And maybe you want to remove that noise from your matrix. So formally, the optimization problem can be stated as follows. You're given some rank parameter k as input, and you're given this matrix A. And your goal is to find a rank k matrix A prime so that A minus A prime is close, meaning that under some norm, A minus A prime is at most 1 plus epsilon times the best possible approximation of A by a rank k matrix. So A sub k denotes the minimum over all rank k matrices of the best possible approximation to A by a rank k matrix. So in particular, let's look at the Frobenius norm. So the Frobenius norm of a matrix, all that is the Euclidean norm of the entries of the matrix. And so what we want here in this optimization problem is to find a rank k matrix A prime so that the Frobenius norm between A and A prime, the Frobenius norm of A minus A prime, is at most 1 plus epsilon times the Frobenius norm of A minus A sub k, where A sub k is the best rank k approximation. And there is a polynomial time algorithm for computing this best matrix A sub k. You can just compute the singular value decomposition of your input matrix A. But that's a very slow algorithm for very large matrices A. So we want to use sketching to speed up algorithms for low rank approximation. And how are we going to use sketching? So the main idea is as follows. We're given this n by n input matrix A, and we're going to choose a sketching matrix S, a random matrix with a very small number of rows. Let's say the number of rows is R, number of columns is n. We compute S times A. S times A, all that does is it takes random linear combinations, a few random linear combinations of the rows of A. Okay, so S times A is a matrix, and think of the row space of S times A, the span of the rows of S times A. There are only R rows. That's an R-dimensional subspace. And what we can think of is A is this n by n matrix. Each of the rows of A we can think of as points in R to the n. And we can project all of the rows of A onto this very low-dimensional space, S times A. And now what we can do is we can find the best rank k approximation to the projected points inside of this low-dimensional space, S times A. And we can do that exactly using the singular value decomposition. So what we did is we still have n points, but they lie in this much lower dimensional space now, this r-dimensional space. And the singular value decomposition in this low dimensional space would take n times r squared time. And so that's a significant improvement over n cubed time for the singular value decomposition in the original space. So the idea is a dimensionality reduction. Now why does this matrix, and so now you get a best rank k approximation to the points inside of the space, and that turns out to give you a 1 plus epsilon approximation for the low rank approximation problem. And there are various different sketching matrices S that you can use, and probably not surprising by this point is that the most time consuming step of this algorithm is actually just computing the matrix-matrix product, S times A. And it turns out you can go through the same sequence, the same thought process. You can choose S to be a matrix of IID normal random variables. That would work. You can choose S to be a fast Johnson-Lindenstrauss matrix. That would work. And the best parameters can be obtained by choosing S to be a count sketch matrix. That would also, all three of these would have the guarantee that if you solve the problem in this low dimensional space, you'll get a 1 plus epsilon approximation. Okay, so there is one caveat about this, which I kind of hid, which is that you compute S times A very quickly. The matrix-matrix product, S is a count sketch matrix, you can compute that very quickly. The problem is you have to project all your input points, all the rows of A, onto this low dimensional space. So what is the current algorithm that we have? The idea is we can compute S times A very quickly using count sketch. Then we project the rows of A onto this space, S times A. And then we find the best rank K approximation of the projected points using the singular value decomposition, which is now efficient since we're in a low dimensional space. Okay, but I didn't say how to project the rows of A onto S times A. That might be very slow. It turns out that you can, the bottleneck here is step 2. There is a fast way of solving this, and I'll just briefly mention the intuition here, which is that instead of performing this projection exactly, you can think of the projection itself as being another instance of regression. So what do we know? We know the row space of S times A, the span of the rows, contains a good rank K approximation. That's what I've been claiming, and that you can show. So therefore, there is some matrix X for which X times SA minus A is a good rank K approximation, right? Because X will just give me some linear combination of the rows of S times A. So I can choose the best such X. Well, this problem is just another instance of regression. Except now this B vector is a matrix. And now instead of X being on the column side, on the right-hand side, it's on the left-hand side. But it's still another instance of regression. And you can use sketching to solve this problem itself. So instead of doing the projection exactly, you can solve this least squares problem using sketching again. And so the idea would be to right multiply by a sketching matrix. Right multiply SA by a sketching matrix R, right multiply A by a sketching matrix R, and now solve that problem exactly. So this reduces the problem, the dimension of the projection problem, and allows you to solve it efficiently. It turns out that the solution has this following closed form. So if you want a low rank approximation to your matrix A, here is a low rank approximation. Choose random sketching matrices R and S and compute the following product. So A times R is the left factor, S times A is the right factor. So AR is a tall thin matrix, SA is a wide fat matrix, and there's this very small matrix in between, which is it's the inverse of S times A times R. So this will give you a low rank approximation. Okay, so just in summary, so I'll just summarize what we've discussed, and then I'll mention some other problems that we have results for, and then I'll mention some open questions. So in summary, we gave fast sketching-based algorithms for some well-studied numerical linear algebra problems, least squares regression, the least absolute deviation or L1 regression, and the low rank approximation problem. And not only does sketching improve the time complexity of these algorithms, it's also very useful in a distributed setting when you have your data partitioned across multiple servers, because the sketching reduces the size of your input instance. And so now if you have data that's distributed, instead of collecting all the data on a central server, you can send the sketch of the data from each of the local sites. And this gives a more communication efficient solution. So that's what we discussed. There are many other applications of sketching, which is why I titled this talk Sketching as a Tool for Numerical Linear Algebra. You can use sketching to solve high precision regression. So in the least squares regression problem I mentioned, there's a polynomial dependence on 1 over epsilon, where you're trying to get a 1 plus epsilon approximation. This is no good if you want machine precision, like if you want a very small value of epsilon. It turns out you can use sketching to get a logarithmic dependence on 1 over epsilon for least squares regression. So you can significantly improve that dependence. There's polynomial fitting. So in many cases, your least squares regression problem, your matrix A has a very special structure. For instance, if you're trying to fit a polynomial, a curve to a bunch of points, your matrix A is a Vandermonde matrix. It has a very special form. And for that, you can actually achieve algorithms that are faster than the input sparsity of your input matrix A, using the structure of the matrix. For low rank approximation, there are other forms of low rank approximation called CUR decompositions, where what you want is you want to approximate your matrix A by a subset of columns of A times a subset of rows of A. So C is a subset of columns of A, R is a subset of rows, and you have this small matrix U in the middle. And you want to compute CUR so that this provides a low rank approximation. So this is useful in low rank approximation problems because it gives you more data interpretability. I mean, if you know that, for instance, if your data matrix A, the rows correspond to people and the columns correspond to attributes, if you know that your low rank approximation is spanned by 1 over square root 2 times the income of a person plus 1 over square root 2 times the age of a person, that might not be very meaningful. On the other hand, if you actually have a subset of columns, then you might have the age column, the income column. It's more easy to interpret your data. There are also kernel transformations that are useful. Sometimes your matrix A, you can think of the rows as n points, and the dimension, what you want to do for each of the rows is apply some function to it to send it to some completely different space. So you want to replace each row with a function of that row. And you want the low rank approximation of that matrix. And sometimes you expand the rows into an infinite dimensional space. You can't afford to explicitly write down f of A. So can you still get a low rank approximation without actually expanding and computing f of A? And it turns out you can do this for certain kernel transforms. So just to conclude with some open questions. So one of them that I mentioned in the talk is that for the sketch and solve technique that worked for least squares regression so easily did not work for L1 regression because we don't know of sketching matrices which work. So we think that there should be a lower bound, that there should not be such, for all known matrices for sketching L1 regression, we can show they don't give a 1 plus epsilon approximation, but we don't know if this is true in general. You can also ask for low rank approximation with respect to other norms. For instance, instead of taking the Euclidean norm of the entries of your matrix, you could take the sum of absolute values of the entries of your matrix. This might be a more robust version of low rank approximation, in the same way it was a more robust version of regression. We don't know of any algorithms. We don't know of any algorithms or hardness results for this problem. any polynomial time algorithms, much less input sparsity time. Another thing you could ask for is low rank approximation with respect to the spectral norm or the operator norm instead of the Frobenius norm. And here we don't have input sparsity time algorithms either. So that's all. Thank you.
David, I'll open up the floor to questions.
Yeah.
Okay, so I've actually two questions. You can choose which to answer both. So one would be, there are many applications where A is not sparse, but you can apply A fast on any arbitrary vector. So and you're not really set up for that. And then a totally unrelated question. Sorry, I'm greedy here. So you have a much broader class of random variables that are stable, for which you have these more generalized relations that you have exploited for L1. So you have Levy distributions that
Exactly.
any exponent. So have you guys looked around to
Yeah.
push it further?
So that has been done actually. So for the second question, you can use p-stable random variables to solve LP regression. For any p between 1 and 2, there exist p-stable random variables, and they'll give you very similar parameters, and the proofs are roughly the same as for L1 regression. For LP regression for p greater than 2, there don't exist p-stable random variables, but what you can do is instead use reciprocals of exponential random variables, and what these do is embed LP into L infinity. So instead of taking an LP regression problem and reducing it to a smaller LP regression problem, you take a LP regression problem and reduce it to a smaller L infinity regression problem using the max stability of exponential random variables. And that has also been done, and it's the nice thing about reducing to an L infinity regression problem is you can solve that using linear programming as opposed to LP regression, which is in general is a convex programming problem. For the first question, if you have A as a black box and you can multiply A by vectors quickly, you may be able to compute S times A quickly if you have that property. For each of the rows of S, you can compute S times A very quickly. But I haven't seen any sort of, well, I mean, this also is related to the kernel transformations that I mentioned. So basically, if I have two vectors and I want to compute their inner product, so that's easy, but what if I want to first expand them, send them to some other space via function f and compute their inner product in that space? So I can do that using the so-called kernel trick. And so that's one way of not explicitly expanding the rows to a larger space. But I haven't seen anything sort of like a complete body of work on that question. Yeah, I don't know. Did you have any matrices A in mind, or is this just a general?
So Trop has in his paper, for instance, where they look at these block card smarts, they have concatenations of different fast transforms, for instance. So you can.
Oh, you're talking about the sketching matrix S.
No, A.
Oh, A.
You can apply A fast on a vector, right?
Oh, A is a dictionary of sparse, of fast
Right.
things. Yeah, actually, so that actually is related to this polynomial fitting problem, where you're able to do faster than the input sparsity time because the matrix A has a special structure. In the case of polynomial fitting, it's a Vandermonde matrix. In your applications, it sounds like it's a Hadamard matrix, or it's a dictionary of matrices that can be applied quickly. So you might be able to use the same techniques here for that problem. I'm not sure. So.
Okay, let's pause for a moment. So I'm sure there are people who need to head off to other meetings or things. So if anyone wants to leave, that'll probably be a good point. Then we can continue with further questions. Well, people are heading out. Let me ask Zinka.
So it says you use the term preconditioning. I'm wondering if there's also a notion of clustering of singular values or the eigenvalues of the normal form at all. Or, maybe choose a specialist or something like
Oh,
that.
a data-dependent S.
Yeah.
Yeah, I mean,
Is that something that...
well, I mean, the best S would just be the top K singular vectors.
Right.
I mean, and that would...
expensive. Yeah.
That's very expensive to compute, yeah. So I don't know, I mean, these are already giving sort of input sparsity time, which is required of any algorithm. Maybe in some situations, if you're given singular vectors more quickly, you can speed that up, but and actually for this L1 regression problem, it turns out that if you choose S to be a function data dependent of your input matrix A, then you can get a 1 plus epsilon approximation by reducing the dimension. So it's really a question there of the obliviousness of S to your input. Does that cause you to no longer be able to obtain a 1 plus epsilon approximation?
Anyone else? Any further questions?
The question? Yeah.
Pragmatically, the last question. Have these techniques ever applied to real-world data and led to grief because there was just too much internal structure in the underlying matrix? It didn't lend itself to the approximation.
Can you say it again? So there's some matrices A which are not...
Well, intuitively, approximations would be great if there's a lot of linear interdependency among the rows and columns of A. And as you said at the top, few singular values are fine, the best approximation. But if you're in a situation where if you did a full SVD of A and there's almost no diminution of the singular values,
Yes.
it's pretty damn complex, and all has to be there. Would these techniques lead to unsatisfactory results if you apply them?
I mean, like the optimization problem is stated, like you could just output the zero matrix because there would be no low rank approximation in that case. Yeah, so I guess the first question is, what would you want to do to your matrix A? If all the singular values were the same, I mean, you can't hope to approximate it by a low rank matrix. So it would really depend on what.
You have to have some sort of statistical survey of the interdependencies in your data before you would proceed with applying such techniques.
Yeah, you would need first to formulate a problem though, like what notion of approximation that you want. Yeah, I don't know of. Yeah, I mean, there are some things like writing things as a low rank approximation plus a sparse matrix is like robust PCA. And there, under certain conditions of your input matrix A, you can actually solve that efficiently. Yeah, in general, if you just have an n by n matrix, yeah, so that does capture some of the structure, like the sparsity. That's all I know of.
Any further questions? Okay, well, let's thank our speaker.